Hello everyone, welcome to my YouTube channel. So today we are gonna simulate ethyl benzene production process using Aspen PLUS. So let's start with it. Okay, so the first step involved in simulating any process is to specify the components that are involved in the process. So first we will specify all the components. So let's do that. Okay, the first component we have is benzene. Okay, benzene. Second, we have ethylene. Okay. Okay, let's find the other components. That is ethyl benzene. C8H10. Okay. Okay, so this is ethyl benzene. Add component. Add. Okay, we press yes. So and the fourth component is diethyl benzene, C10H14 D2. Okay, so this is diethyl benzene. We will add this. Okay, so now we have added all the components that are involved in this process. Okay, the second step is to specify the thermodynamic model. So we will go to the methods and let's I have already selected NRTL, so let's remove this. Okay, and now we will go to specifications. Okay, we will select the Chow-Cedar property method. Okay, so this is Chow-C. Okay, so this is selected. Okay, so we are all set now. Now we will go to the simulation. Okay, let's do one thing more with the components to make it more understandable and recognizable. So we will rename them. Okay, so this is benzene, ethylene, and this is EB, ethyl benzene. Okay, we will press rename. Okay, and this is diethyl benzene, DEB. Okay. Okay, now we are all set. Okay, so let's first we will add all the equipments that are involved in the process. Okay, let's do that. Mixer. Okay, one. Then we have a pump. Then we have a mixer. Next two. We have a compressor. We have a heat exchanger. Then we have a reactor, CSTR. Another CSTR. columns. Another column that is for the product. Okay. So we have a one mixer here. Okay. So now connect all these equipments. Material. Connect this. It's benzene. Another stream. Ethylene. Connect this to the phone. Its name is 1. Okay, we will arrange these equipments, make them align. Okay, so we have aligned all the components, all the equipments. Okay, now we will specify the operating conditions. So let's start with the benzene stream. Okay, so we have 25 degrees Celsius temperature, 1 atm pressure, 1 atm. and we have a molar flow rate of 630.6 kilomoles per hour. Okay, we have the mole fraction here for the benzene, that is 1. Okay, then now we will specify the operating conditions for the ethylene stream. So we have the same conditions: 25 degrees Celsius, 1 atm pressure, and 630.6 kilomoles per hour. And we have mole fraction for ethylene, that is 1. Okay, now we will specify for the pump. So we have a discharge pressure of 20 atm. Okay, and we will also pressurize the ethylene stream to 20 atm. Okay, so the compressor model type is isentropic, and we have discharge pressure, that is 20 atm. Okay, so, and we will cool down this ethylene stream to 169 160.9 degrees Celsius, and the pressure is 2016 kilopascal. Okay, now we will specify the reaction conditions for the CSTR. Okay, so we have a pressure of 19.15 bar, and temperature is 160.9. okay, and the violet phase is or liquid only, so because this is a liquid phase reaction. Okay, and the reactor volume is 200 cubic meters. Okay, we'll go to this reaction tab. Okay, so we first specify the reactions. Okay, for that we will go to the reactions there. Okay, click on the new, and select type is power law. Okay, new. Okay, so the first reaction is benzene react with ethylene, and the coefficients are -1, -1. Exponents for these components are 1, 1. Okay, the product is ethyl benzene, EV. The coefficient is 1. Okay. Okay, the second reaction is ethylene react with ethyl benzene. The coefficients are -1, -1, because these are consumed in the process, so we add the negative sign, and the exponents are 1. Okay, the product is diethyl benzene. Okay. Okay, the third reaction is benzene that react with diethyl benzene. The coefficients are -1, -1. Exponents are 1, 1, and it produces ethyl benzene. Coefficient is 2. Okay. Okay, we will now go to the kinetics. Okay, so for the first reaction, the reacting phase is liquid, and red bases are selected as reaction volume. Okay, so we have K value for the first reaction, that is 1.528 10 raised to the power 6. Okay, and we have the activation energy, that is 17,000, and the unit is calories per mole. Okay, now we will go to the second reaction, and for the second reaction we have a K value of 2.778 10 raised to the power 7. We have activation energy, that is 20,000 calories per mole. Okay, now we will go to the third reaction, and for the third reaction we have 1000 K value, and the activation energy is 15,000 calories per mole. Okay, so we have specified the reaction conditions and the kinetic parameters for these reactions. Then now we will go to the CSTR, and we will go to the reactions tab, and we will add the reaction set here. Okay, now we have all set for the first reactor. Okay, now we will go to the second reactor. Okay, and for the second reactor we have pressure of 1840 kilopascal, and this reactor is operated adiabatically. So we will specify the duty here 0. So the operation is adiabatic, and we have a reactor volume same as the previous one, that is 200 cubic meters. Okay, and the reaction set is R1. Okay, we will change the valid phases to liquid phase only. Okay, so now we have specified the condition for reaction 2. And now we have expansion valve here, so we will specify the outlet pressure for this valve, that is 152 kilopascals. Okay, now we will configure this recycle column. Okay. So we have total number of stages 21, and condenser type is total condenser. We have a distillate rate of 969.4, and we have reflux ratio of 0.774. Okay, we have the feed stream location here, that is 10 number stage, and the feed enters on stage. Okay, we will specify the condenser pressure, that is 30.4 kilopascal. We have condenser pressure drop, that is 2 kilopascal. And we have column pressure drop, that is 68 0.9 kilopascal. Okay, so we have set all the conditions for the distillation column. Okay. Okay, now for this column we will specify some design specifications. So we will go to the specification tab under the column 1, and this is the design specifications. Okay, we will select new, and here in the type we will select the mole purity, and we will enter the target 0.999. The components is benzene, and the product stream is benz. Okay, we will go to the vary. So we will vary the reflux ratio to get the desired mole purity for the benzene. Okay, so we will vary the reflux ratio. Yeah, this is reflux ratio, and we have the lower bound for the reflux ratio, that is 0.01, and we will set the upper bound 5. Okay. Okay, now we will set up the second column. So we have total number of stages 25, condenser type is total, and we have a distillate rate of 282.2 kilomoles per hour, and we have a reflux ratio of 0.9. Streams section, we have a feed location at 10. We will now specify the pressure. Okay, so the pressures for the condenser is 10.13 kilopascal. And condenser pressure drop is 2 kilopascal. And the column pressure drop is 89.17 kilopascal. Okay, so we have specified all the things. So let's do two things more. We will add a recycle streams. Okay, so we will recycle this benzene to the process. For that we will add pump here, and another pump here. Okay, we will flip this. Also this one. Okay, now we will click on this benzene stream, and we will reconnect this to the pump here, and we will connect this to this mixer. Okay, we will name them as benzene recover. Okay, now we will select this one, reconnect here, here, Okay, we will specify the pressures. So the discharge pressure is 1915 kilopascal. Okay, and for this pump we have discharge pressure 1.3 kilopascal. Okay, okay guys, we have completed the flow sheet. Okay, so we have made a mistake here. We added this a distillate rate of 282.2 kmols per hour, but this is the bottom's rate, so we'll change this to bottom's rate 282.2 kmols per hour. Okay, now we have all set. Okay, so let's do something before we go to run this simulation. Okay, we will first go to this column 1 and we will go to the convergence. Okay, so here we have maximum iterations are 25, so we will increase this to 200 because we have some 2 recycle streams, so we need some more iterations to converge the flow sheet. Okay, similarly we will increase the iterations for the column 2. Okay, we will also increase to 200. Okay, and we will, for the whole flow sheet, we will increase the convergence here, options, methods, and here it is 30, so we will increase this to 500. Okay, and we will also add the tear streams. So we have 2 tear streams. One is the benzene recycle and the other one is DEB recycle. Okay, no, so now we have all set and we will run the simulation to check whether our flow sheet converges or not. Okay, so we will run this. Okay, so our simulation is converged and we have results, as you can see here, results available. So we will check the results for this column 1 stream results. And you can see here we have mole fractions, so we get 99.9 mole percent benzene, which is recycled. Okay, and for the column 2, that is for the product, to get the product, we will see the results. So you can see here we have 99.8 mole percent ethyl benzene. Okay, so we get 99.8 mole percent pure benzene from this process with a total molar flow rate of 630.6 kmols per hour. So if you see, we have specified the benzene and ethylene molar flow rates at 630.6 kilomoles per hour. So we get the ethyl benzene also at 630.6 kilomoles per hour, which shows that this process has a zero discharge process. Okay, So we recycle the diethyl benzene in this process to this second reactor, and this second reactor converts this byproduct again to ethyl benzene. Okay, so this is the zero discharge process.